Why is the ocean so salty? Because the land doesn't wave back. Mr. Whited here, and I wanted to do a little voiceover for this PowerPoint I presented to you because this week is all about waves. And believe it or not, there's not a whole lot of wave jokes available on the internet. Trust me, I searched. So that was probably one of the best ones I can come up with. So sorry about that. All right, so I am actually in the PowerPoint that I put online on Canvas, and I just wanted to kind of talk you through some of the slides really quick. This week was a very basic introduction. When we come back from spring break, you guys are going to spend a little bit more time digging deeper into waves and what our waves are all about and the science behind it. Okay, so here we go, waves intro. So what is a wave? Well, hopefully you did that little activity on Monday. If not, you still have time. Go back and do it from the beginning. You were asked to come up with some ideas and examples of waves. So you may have come up with ocean waves, sound waves, maybe light waves, maybe waving your hand, right? Those are all valid examples of waves. I think ocean waves is one of the ones we kind of think about a lot. Earthquake waves might be something, but they all have something kind of in common. They are disturbances that transfer energy from place to place. Remember, energy is not matter. Energy are all those things like sound, light, electricity, the Mrs. Sense, mechanical, radiant. They transfer energy from place to place. What's important there is they transfer energy, but not necessarily the particles that the energy hits. And we're going to kind of dig more into that and what that means. And I'll try to throw some examples out for you when we get to that point. But it's important that you kind of understand just the kind of science definition of what is a wave. So most waves, we can categorize them into two big groups. Okay, we've got electromagnetic waves and mechanical waves. And if you think back to when we looked at electromagnets, you may remember that an electromagnet is something that uses electricity and magnetic fields to kind of play off each other. If you remember, I had the battery with the copper wire on top. We looked at generators and motors and all those things that make our life easier. They're related to these type of waves, right? They're called electromagnetic waves because they use electrical fields and magnetic fields. So we'll get more into that. But I just wanted to point out the wording, right? And you can kind of break it apart and see that there's some relation there. And then of course we've got mechanical waves. And if you think about mechanical, you can remember mechanical usually is the physical movement of something. Okay, so maybe that might help you memorize these type of two groups. And when we talk about specific waves, they're going to fall within these two groups. Okay. All right. So before we look at the groups, and that was kind of your goal this week, was to kind of see the difference between the two groups. We have to kind of look at what a medium is. And I'm sure we've talked about mediums in class before, but just to kind of throw that out there again because it's important. So a medium can be anything that's matter. So anything that has mass and volume. So examples can be water, air, metals, walls, pretty much anything you can think of that can be either a solid, liquid, or gas, okay? Even plasma, which is ionized gas, right? Those can all be considered a medium. So that's very important to keep in mind. So this is kind of the famous experiment that maybe your parents might have done, is you can actually take a can and you can put a string up to it, and then you attach a can on this other side. If you have time and you're bored, might not be a bad little experiment to do at home if you have the materials. And you can kind of, if you have a long string, you can see how far you can hear each other, and that'll help you kind of understand what a medium is, because this medium would be this can and the string, and of course the ear too as well. And what you'll be hearing is sound waves. All right. So, but we'll get more into sound waves specifically later. So here is an example of an electromagnetic wave. Now, on your sheet, your Venn diagram, I asked you guys to write down things specific to each one. So here's all about electromagnetic waves. So it does not need a medium. Remember, so it does not need those solid liquids or gases to travel. It can actually travel through space. Because in space there's not a lot of mediums available. So when we look at mechanical waves, you're going to find that they do not, right? But electromagnetic waves, they do not need a medium to travel through space. So some examples include light, radio waves. So we're going to get into, and then also our visible spectrum, what we actually see in terms of light, is also considered in electromagnetic waves. But all those types of waves, UV rays, uh, which is ultraviolet. We're going to look at X-rays and things like that, right? And those are all part of this electromagnetic wave group. So they travel as a disturbance of electric and magnetic fields. So again, kind of going down and breaking down the actual word itself. So they have electrical and magnetic fields, and that's what actually allows them to travel through space without needing a medium. I'm not going to get into the specifics because it gets into the complicated nitty-gritty of physics. But if you see here, you see red and blue. Well, one side of that's magnetic and one side of that's electric. And those two are kind of playing off each other. And when they do that, they're propelling themselves forward. So this kind of wave, if you imagine this is a wave traveling through space, and then eventually it gets to Earth, traveling from the sun, our sun, which takes about 7 minutes approximately. And I know we talked about that in class. Which brings me to this part. They tend to travel very fast. Matter of fact, in space, the speed of light, which is an electromagnetic wave, travels at 186,282 miles per second. So miles per second. So as far as we know, that is the fastest thing that we know of. Okay. Now, of course, everything changes in science, but as of right now, that's the limit of where our science can go. Most of our equations, they are stuck with that being the limit. And these type of waves are what's called a transverse wave. So when we get back from spring break, we're going to look specifically at what a transverse wave is. And simply, just to kind of give you a preview, you see how it kind of goes up and down like a roller coaster? Ooh, up and down, up and down. That's called a transverse wave. So it has this kind of shape to it. All electromagnetic waves are transverse. So make sure you can put that into your Venn diagram. All right. On the flip side, we have mechanical waves. Now, mechanical waves requires a medium to transfer energy. So mechanical waves will not travel through space. They do require a medium. So they do require some sort of solid, liquid, or gas in order to travel. They require some sort of matter, right? So some examples include sound waves, ocean waves, and earthquake waves. Those are all types of mechanical waves. They are a lot slower in speed compared to electromagnetic waves. So for instance, sound waves travel approximately 761 miles per hour. So that's quite a bit slower than a light wave. That's why it's actually possible for us to actually break the speed of sound. You may have heard that. And I may post some videos about jets breaking the speed of sound when we get specifically to sound. And they make this very specific sonic boom that you can hear, which I think is very interesting. If you've ever been to an air show, you may have heard if you've seen jets traveling very fast. And so whereas electromagnetic waves are transverse, these types of waves tend to be longitudinal and they can be transverse. Okay, so they can actually be both types, whereas electromagnetic waves are only transverse waves, right? They have this kind of roller coaster effect. Longitudinal is a little different. So here is kind of an example of longitudinal. And if you kind of think of like if you're staring maybe at the ocean from the top, and these are kind of waves moving past you, right? And they're kind of pushing, and these little black things are all the little particles. So kind of like little objects. All right, and notice what happens to these particles as they push. So they kind of move a little bit, but then they go back to their original point. So those particles never really move any further than it is. That's what a longitudinal sound specifically is going to be this type of wave, except it's going to kind of go out in all directions, right? All directions around you. But sound is a type of longitudinal wave, and but you may say, well, Mr. White, if ocean waves are mechanical waves and particles don't necessarily move, well, how come particles end up coming up to shore? Well, ocean waves are kind of special because remember I said mechanical waves can be longitudinal and transverse. Well, ocean waves are a combination of both, and because it has that transverse in there, it kind of forces those particles to move. But don't get too caught up on that. I just wanted to point that out. So don't get too confused. Just spend time focusing on what's the difference between a mechanical wave and electromagnetic wave. And if you have specific questions, I'd be more than happy to answer them. I think that might be it. So very simple. Hopefully this helps you, because I know it's hard for it's hard for students to be at home teaching themselves, and I get that. And it's hard for me to kind of get online and be able to talk to every single one of you. So hopefully, if you're able to watch this video, you can kind of get a feel for what we're learning, and maybe you understand a little better. So this week, like I said, just focus in on what's the key difference between the two major groups of waves, and everything's listed here in the PowerPoint that you need to know. Okay. When you guys get back, we're gonna focus in on specifics, anatomy of the waves. So, for instance, um, those terms like crests and trough and wavelengths and frequency and all those things. Those are all going to be, we're going to start learning a little bit about that. So we'll get through it. I hope everybody has a safe week. Please email me with any questions. Take care. Bye.